Hello again, everyone. This is Mr. V. Hill, and today we're going to be talking about graphing quadratic functions. So let's start off with a little bit of review. Basically, the standard form of a quadratic equation or a quadratic function is always going to look like this. Your dependent variable y is going to equal some number a times the independent variable x, but this x is going to be squared. The squaring right here is what makes it quadratic. But then to that quadratic term, we're going to add on number b times x. This is what we call the linear term. Because, well, I've seen this, well, take off the x squared term, now we see something that looks very linear. Bx plus c, which is just like mx plus b. We just use different letters for no good reason. But anyways, a times x squared plus b times x plus some other number c. This is what we call the constant term. And of course, for this thing to be a quadratic equation, this first number a, well, that can't be 0. Because if it were 0, 0 times anything is 0, and, well, now we're back down to a linear equation. But we've looked at these things already, and we know that when we do graph a quadratic function or a quadratic equation, what we get is called a parabola. It's that nice U-shaped curve. So basically, the whole idea here again is that this equation is the name for a collection of points in the plane, and that set of points just happens to form that parabola shape. Okay. So back during the first semester, we were doing that big graphs activity. We mostly only looked at equations that look like this. Y is equal to a times x squared plus c, where we didn't have this linear term, the b times x. Or in other words, that means that b was equal to 0, because 0 times anything is 0. We don't need to write that in there. And we looked at various graphs, and we saw how changing this a and this c changed the appearance of the graph. And what we found was basically this. If that a was positive or greater than 0, the parabola is going to be opening up like this. And the vertex of the parabola is going to be a minimum value. The y-coordinate of the vertex is going to be the smallest possible value of x, or excuse me, of y. Or if a was negative, less than 0, the parabola is going to open down like this, and the vertex turned out to be a maximum. That y value is the biggest value of y that we have in the set of points. So a affected whether the thing opens up or opens down, but also if the absolute value of a is bigger than 1, then the parabola is going to be steeper than the parent function y equals x squared. And if the absolute value of a is less than 1, then the parabola is going to be less steep. Oftentimes you hear people referring to the steeper parabola as being more narrow than the parent function, but that's a really bad way of thinking about it, since this a is actually affecting the parabola vertically. It's stretching the parabola out or squishing it down to the x-axis. We often say that the less steep parabola was wider, but again, we don't want to think about the parabola getting wider. We want to get it less steep. So in that way, we can think of that a is a very, very similar to slope for linear equations. For c, what we saw was if c was bigger than 0, then the parabola was shifted up. Because the parent function y equals x squared, that had its vertex at the origin. If we add on a positive number, then that just shifts the parabola vertically up above the x-axis. Or if c is less than 0, that's a downward shift. Actually, it's called a translation if we're looking at it as a transformation of points. But actually, c also gives us the y-intercept, because the y-intercept occurs where the x-coordinate is 0. So if we plug in 0 for x, the resulting y value will be the y-intercept. But if we plug in 0 for x, a times 0 squared is 0, b times 0 is 0, so the whole thing just becomes c. So the y-intercept will have coordinates 0, c. So the big thing to really get out of this, basically, is that these two equations, y is equal to a times x squared plus c, it's very similar to y is equal to mx plus b. These things are analogous to each other. The only difference being the x is squared in this equation, x is not squared in this equation. This is the equation of a line, this is the equation of a parabola. But the steepness of the parabola is given by a, and the y-intercept is given by c. Whereas here with the line, the steepness of the line is given by m, the slope, and b is the y-intercept. Same kind of thing. So that's kind of an important thing to understand. Now for b, that's a little bit different. That's where really the interesting stuff starts to happen. Because if we look at various equations like y is equal to ax squared plus c, let's just graph a few of those. Start off with just the parent function y equals x squared. Okay, let's do 3 times x squared. Let me do maybe 0.25 times x squared. Maybe we'll add on a c here, plus 3. And let's do maybe 0.5 x squared plus negative 3. And we'll graph all of those and see what they all look like. There's a second one, third one, and the last one. So what we'll notice here, they're all various steepnesses. This one is shifted up, we got one that's shifted down, but all of these parabolas are symmetric. And the line of symmetry for the parabola is, of course, the y-axis right there. So any quadratic equation where the b is 0 is going to have a line of symmetry, which is the y-axis. If b is not 0, then that's going to change the line of symmetry. Or let's abbreviate that as LOS, because we're going to be referring to it quite a bit. If b equals 0, then the line of symmetry is the y-axis. Okay, so let's work through a couple of examples about how to graph these things. But first, we're going to have a basic strategy. So the first thing we want to do when we're graphing these quadratic equations or quadratic functions is we need to plot that line of symmetry. And luckily there is a formula for finding that line of symmetry, and it's given right here. X is equal to negative b over 2a, where a is the coefficient of x squared, b is the coefficient of x, and well, c doesn't appear in that formula for the line of symmetry, but c is just the constant term. So once we figure out what the line of symmetry is, we'll notice that's x equals a number. That's going to be a vertical line. So all quadratic equations are going to have a vertical line of symmetry. Once we plot that, then we're going to plot the vertex. Nice thing here is that the vertex always occurs on the line of symmetry. So all we have to do is plug in this value for x in the equation, and what pops out is going to be the y-coordinate of that vertex. Pretty simple. Once we plot the vertex, then we plot the y-intercept, which is just given by the coordinates 0, c, because c is, of course, the y-intercept here. But using symmetry, we also will get its buddy point on the other side of the line of symmetry. And we'll go through an example showing that. And then what we need to do is just get enough points that we can sketch a decent curve. Or there's an idea about slope using this number a that we'll talk about here in just a second. Basically here, if we're plotting a line, you only need 2 points to graph that thing. For a parabola, all you need are 3 points. 3 points to determine a unique parabola. But oftentimes 3 points won't really give you a good idea of what the parabola really looks like. So you got to plot a few more points. But let's just do an example here. Example 1, y is equal to 3 times x squared. And down here what I have is the parent function already graphed, y equals x squared. And just so we can compare the two. So, first thing we want to do is plot the line of symmetry. Before we do that, though, we might notice here, we just identify exactly what a, b, and c are in this equation. So here, a is equal to, well, the coefficient of x squared, which is 3. B is equal to 0, since there's no b times x up here. And also c is equal to 0. If we identify those values first, it'll save us a lot of grief. And so we might want to just think about this. Notice here that a, this 3, is, well, bigger than 0, so we know that the parabola is going to be opening up, and the vertex is going to be a minimum. Since 3 is bigger than 1, we know that the graph is going to be steeper than the parent function y equals x squared. Given that c is 0, we also know that the y-intercept is going to be the origin, 0, 0. And so, let's see here. First off, the line of symmetry is going to be given by x is equal to negative b over 2a. B is 0. A is 3. But of course, 0, the negative of 0 is 0, 0 divided by 6. That's still all just 0. Of course, the y-axis. Since b is 0, that means that our line of symmetry for our parabola is going to be the y-axis, just as it is the line of symmetry for the parent function y equals x squared. So that's already put in there for us. Great. Now, the y-intercept is given by the point 0, 0. That's the origin, which is on the line of symmetry, of course. But that's also going to be the vertex. So I can put a dot there. So we just plug in this value of x for x here. So 3 times 0 squared. The y that we get out is also 0. So the y-intercept is the origin, and that is also the vertex of our parabola. So now, let's see here. So we've plotted the line of symmetry. We've plotted the vertex. We've actually also plotted the y-intercept. But since the y-intercept is on the line of symmetry, we don't get a bonus point out of this with a symmetric point. So now we just need to either plug in some values of x, easy ones like 1, negative 1, 2, that sort of thing, and plot a few more points. Or what I like to think about is this idea of slope. And so check this out. With your parent function y equals x squared, this standard ordinary parabola, the steepness of it, you can kind of think about this. As you move away from the vertex, if we move over 1 unit, to get back onto the parabola, we have to move up 1 unit. Because, of course, when you plug in 1 here for x, 1 squared is 1. So you can think about going over 1, up 1. On the other side, we're doing the same thing. To the left 1, we would also go up 1. Because if we plug in negative 1 for x, the square of negative 1 is a positive 1. So the regular steepness kind of goes over 1, up 1. But then, remember, this is not a line, so it doesn't go over 1, up 1 again. We have to think about going over 2 from the vertex. And then we would go up 1, 2, 3, 4 to land back onto the parabola. Because if we plug in 2 for x here, 2 squared is 4. So over 1, up 1, over 2, up 4. Same thing to the left side. Over 2, up 4, because the square of negative 2 is also 4. If we go over 3 from the vertex, then we'd have to go up all the way 9 units. Because if we plug in 3 here, 3 squared is 9. Over 1, up 1, over 2, up 4, over 3, up 9. Same thing over here. Over 1, up 1, over 2, up 4, over 3, up 9. If we were to move over 4, then we'd go up 16. Right? Because you're always moving up by the square of however far you've moved horizontally. Now for this parabola, though, y is equal to 3x squared, all those vertical motions are going to be multiplied by a factor of 3. So instead of going over 1, up 1, we go over 1, up 3 times 1. Right to there. Same thing on the left. Over 1, up 1, 2, 3. Because we're multiplying the vertical distance by 3. If we go over 2, we would normally go up 4, but since a is 3, we're going to multiply that vertical distance by 3, so it'd be over 2 up 12, which is going to be way up here about. And the same thing is going to happen on the left. Over 2 up, instead of 4, we go up 3 times 4, so all the way up to 12. And we see we've got a, now that's pretty good. We can kind of see how this curvature is going to happen. And keep in mind that parabolas do not have pointy parts at the vertex. They're nice and curved. And so we just kind of sketch in this nice little U shape. And now we have our parabola. You could, of course, just plot a few more points here. Plug in 1 for x. 1 squared is 1 times 3 is 3. So you know the point would be 1, 3. Plug in 2 here for x. 2 squared is 4 times 3 is 12. 2, 12. No big deal. But when the vertex is not at the origin, I kind of like just think about this slope idea. It's helped me out a lot. And of course, we can check this in our calculator if we want to look at it. So let's clear out these other ones. Oops, actually I did have 3x squared in here. And if we graph both of those, there's a parent function, and there is y equals 3x squared. Clearly, parabola opening up, vertex at the origin, 3 times as steep as the parent function. Let's try another example here. This one will be y is equal to negative 1/4 times x squared plus 5. So looking at this now, right off the bat we know that the parabola is going to be opening down because a is a negative number. We also know that the graph will be less steep than the parent function because negative 1/4 in absolute value is less than 1. So first off, let's just start thinking about this. First off, our line of symmetry is going to be given by, well, since b is 0, we know that's going to be the y-axis, which I've got plotted already right here. Great. If we wanted to, we could figure it out by x is equal to negative b, which is 0, over 2 times a, which is negative 1/4. But of course that 0 just kills everything off, so x equals 0, right? Might have wanted to point out here, a is equal to negative 1/4, b is equal to 0, and c is equal to 5. So let's figure out the vertex. Sorry about that. The vertex, of course, is going to be given by what we get when we plug this value in for x, because the vertex has to happen on the line of symmetry, so the x-coordinate of the vertex is the same as this value here, 0. So the vertex is going to have x-coordinate of 0, and when we plug in 0 for x, we'll get the y-coordinate out. Negative 1/4 times 0 plus 5, or y is equal to 5. So the vertex is the point 0, 5. Great. 1, 2, 3, 4, 5. There's our vertex. And wouldn't you know it, it also happens to be the y-intercept, of course, c. Now what we need to do is either plot a few more points just by plugging in various values of x, or we can use the slope idea. Negative 1/4 is a. So we know the thing is opening down, so however far we move over, we're now going to be moving down instead of up. Normal parabola, if you move over 1, you would go down 1. Here we're going to only go down 1/4. Or 1/4 times 1. And the same thing would happen on the other side. Over 1, down 1/4. Normal parabola, you go over 2, you would go down 4, because 2 squared is 4. Now we're going to multiply that by 1/4, so we would go over 2, down 1. Nice point right there. Same thing's going to happen on the left. Over 2, down 1. And already we're starting to see a little bit of curvature here. Let's go a little bit farther. If we go over 3, we would normally go down 9 because 3 squared is 9. But we'd want to go down 1/4 as much. So 9/4, well, that's a fraction. We don't want to mess with that too much. But if you think about it, over 4 down 16, oh, that's nice, because now 1/4 of 16 is just 4. So if we go over 4, we go down 16 times 1/4, we're down 4. 1, 2, 3, 4. So now we're right at the point 41. And similarly, on the other side, we move over 4, and we go down 4, and we have our point right there. And then we just sketch in the curve. And we see our wide parabola. Really, it's been squished. That is opening down. And there's how we would graph y is equal to negative 1/4 x squared plus 5. If we wanted to check that in the calculator, clear these ones out. Negative 1/4, oops, times x squared plus 5. We graph that, and there's our nice wide parabola, looking very similar to what we graphed on paper. Let's do one more example here. Example 3. Y is equal to negative x squared minus 5x minus 6. First thing we probably want to do is identify what a, b, and c are. So here we have negative x squared, so keep in mind that the negative sign is really shorthand for multiplying by negative 1. So a is negative 1. We're subtracting 5x, so b is actually equal to negative 5. We could switch this to plus negative 5x if we wanted to. C, we're subtracting 6. We could switch that to plus negative 6. So c is equal to negative 6. So, since a is negative 1, the parabola is going to be opening down, or the vertex is going to be a maximum value. It's going to have the same steepness as y equals x squared, because the absolute value of negative 1 is 1. Let's see here. So we could also figure out the line of symmetry here. So the line of symmetry is given by x is equal to negative b over 2a. Now be careful here, because now b is not 0. So the line of symmetry is definitely not going to be the y-axis. But it's negative b, but b is negative 5. So this is going to be the negative of negative 5 divided by 2 times a, which is negative 1. And also, there's a very good reason why this is the formula for the line of symmetry. It involves a little bit of calculus to figure it out, and hopefully we'll have some time in class to talk about that, because I hate to just leave you with, oh, memorize this formula. That's just dumb. But now if we simplify this down, this is going to be the negative of negative 5, which is 5 over 2 times negative 1, which would be negative 2, but we don't want to write that negative sign in the denominator. We always want to put it in the numerator. So the line of symmetry is given by x is equal to negative 5 halves. Or, since we are graphing, this is one of the few instances where writing it as a mixed number is valid. And 5 halves is 2.5, so we want to go over here, negative 2.5, which would be right here, and that's where our line of symmetry is going to be. I'll put in a vertical line in a different color just so we don't confuse it with the y-axis. So there's the line of symmetry. Next, we want to find the vertex. So the vertex always happens on the line of symmetry, so we know that the x-coordinate is going to be negative 5 halves. We find the y-coordinate by plugging that in for x into our original equation. So the y-coordinate is going to be given by negative of negative 5 halves squared minus 5 times negative 5 halves minus 6, which is, of course, well, negative 5 halves squared, that's 25 fourths, but we want the negative of that. Minus 5 times negative 5 halves would be negative 25 halves, but we're subtracting that, so that would be plus 25 halves. And then still subtracting 6. But now, in order to do this addition and this subtraction, now we need a common denominator. So this is negative 25 fourths plus 50 fourths minus 24 fourths. Negative 25 of these fourths plus 50 of them gives us positive 25 fourths. Subtract off 25 fourths and we get 1/4. So the vertex is going to be given by negative 2 1/2, 1/4. And we can plot that. Negative 2 1/2 and up 1/4. So it's just above the y-axis. There's going to be the x-axis. Now we should also plot now our y-intercept, because of course, since the line of symmetry is not the y-intercept, the vertex is not going to be the y-intercept. But that's just given by this value of c, negative 6. So the y-intercept is going to have coordinates 0, negative 6. So we down 1, 2, 3, 4, 5, 6. And there's another point that's going to be on our parabola. But this is kind of nice. We get a bonus point on the parabola just by using the symmetry. So the line of symmetry is at negative 2 1/2. So the symmetric point would be also have a y-coordinate of negative 6, but equidistant over on the other side. So over here at negative 5, negative 6. We get our symmetric point from the y-intercept. And so we could try to sketch in the parabola just like this, but if we wanted to, we could try to put in a few more points just using the whole slope idea. So the slope kind of the parabola is going to be negative 1, meaning it's opening down. But if we go over 1, we go down 1. Over 2, we go down 4. So we go over 1, down 1, that would bring us down to negative 3/4. Over 2, down 4 would bring us to negative 3 3/4. And we have symmetric points on the other side as well. And so now we just sketch in our curve. And again, don't make your parabola pointy at the vertex. and we get this really nice, pretty parabola. And if we want, we can check. Well, that's probably not the prettiest parabola, but hey, we're freehanding it here. But if we check in our calculator, let's see here. So we've got the negative of x squared minus 5x minus 6. We graph that thing, and yeah, we get the exact same picture. And that is how to graph a quadratic function.